Today we're going to focus on modeling with polynomials. Now, just so you know, modeling is sadly not about looking at beautiful people wearing amazing clothes and walking in just a certain special way down a runway, if only. But modeling is about taking real-world data and trying to model that data with a mathematical equation. If you're in my class, we've done this already with linear things, but we're also going to look at it today with quadratic, cubic, and quartic shapes. So we want to fit an equation to data. So these are the basic shapes that we're going to be thinking about. Linear is a straight line, quadratic's a parabola, cubic looks like that, and quartic like that. Now just one side note I want to make sure you know is these all could be upside down or a different direction. In other words, this could be more like this. I know it's backwards on the labels now, but now this is the quadratic. Sorry. And this is the cubic. And the one on the far left right here is the quartic. So one thing you can note is that the number of turns, the number of times it changes direction plus 1 tells you the degree. So in case you don't know what I'm talking about, this straight line, linear is x to the first power. It doesn't ever change direction. If it's going up, it stays going up. There could be going down, but if it's one like that, it always goes down. So it never changes direction. Whereas the quadratic always has one spot where it changes direction. This particular one is going from decreasing to increasing. So it changes direction once. So if you do 1 plus 1, that tells you it's a degree of 2. Quadratic is those that are x squared. Cubic changes direction twice. Goes from up to down, down to up. So it changes direction twice. You add 1 to that. That's why it's an x cubed, because 2 plus 1 is 3. Now quartic changes 3 times. 3 plus 1 is 4. That's why quartic is x to the fourth. So as we're trying to look at data and figure out which of these models will make the most sense, we're going to use how often the data turns or changes direction to help us figure that out. So this first example, we're given these points and asked to write a polynomial function to model the data. So we're going to use our calculator for this. So I have all my data plugged in. So I want to make sure you know how to plug this data in. So when you're just at your normal screen in the calculator, you click Stat, kind of in the middle toward the top. Hit Enter where it says Edit. And then these will be blank normally, but then you can just fill them in. I put all the x values in L1. I put all the y values in L2. So now I'm going to hit second y equals, and I'm going to hit Enter where it says plot 1, because I want to turn this plot 1 on, and I want to make sure this first one is highlighted. This is a scatter plot, so this will help me make sure I can see the points that I just plugged in to the calculator. Also, I'm going to go to y equals and clear out anything I have there, just so it's not in my way, because I only want to see the data points. And if you just click graph, you probably aren't going to see them. Or we just see one of them, the 0, 6. It's because it's outside of the window. You can zoom out and change your window manually, but the easiest way is to go to Zoom. And then if you go to number 9, sorry, I went the wrong direction. If you go to Zoom 9, it says Zoom Stat. So that means it will zoom to fit whatever data we put into the stat. So click Zoom, and then you can just type the number 9 if you want. It's a lot faster than what I'm doing. And it'll automatically fit the window to match. So there we see the data. So the general shape here looks something like this. So that should tell us, since it only changes direction one time that we should probably do a quadratic, because a change of direction once plus 1 gives us 2. So that tells us to use x squared, which is a quadratic. So now, to run that regression, click on Stat, go over to Calc, and the fifth one down is the Quadratic Regression. So we go to number 5, we hit Enter. And I have this listed on the next slide so you can see what to do. But once you come here, you want to make sure your X list is L1, assuming that's where you plugged it in, and your Y list is L2, assuming that's where I plugged it in. And we're going to want to graph this so we can see how well it fits. So where it says Store Regression Equation, make sure your highlighter is there, your cursor. Then go to VARs, which stands for variables. It's just to the left of clear. Go over to Y variables. Click on, hit enter on function, hit enter on Y1. So what that'll do is once it finds the equation that models this data, it'll plug it into the graph for us, so we don't have to retype the whole thing. We hit calculate, and there we have it. So they tell you the general form, ax squared plus bx plus c, and they tell you what a, b, and c are equal to. So 4 goes with a, so it's 4x squared minus 2x plus 6. So that's how we write the answer. 4x squared minus 2x plus 6. And those are pretty exact numbers. That's because that's exactly correct. If we look at the graph, it's going to go exactly through the points. Now this won't happen real often. Most of the time it'll go through most of the points but miss some of them, because in real world data it's almost rarely a perfect equation. So one other thing we can do to know how well does this fit. Like if I did a straight line, that wouldn't fit it very well. So let's go to, I think it's under Mode, and go down to if you're on a color calculator, it's all one page, but if you're on an 84 plus or 83, it's down on the second page, or just an 84 plus actually, where it says Stat Diagnostics, turn that on. And once you turn it on, it should just stay on. You don't have to do this every time. Just turn the Stat Diagnostics on, leave it on. So if I run the exact same regression again, you'll see the same numbers for A, B, and C, but you'll also see an R squared at the bottom. R squared tells me how well this fits the data. If R squared is equal to 1, it means it fits it perfectly, truly perfectly. More often, you'll see decimals, because R squared can be anything between 0 and 1. A 0, you probably never see that, but that would mean it doesn't fit the data at all. It's a terrible, terrible fit. If you see something like 0.7 or higher, that means it's a pretty good fit. Maybe like 0.3 to 0.7, it's a little bit of a fit, but not very good. Below 0.3 is just a terrible fit. Now, just so those of you who are watching know, I'm basically just choosing those numbers. A different teacher may feel differently and choose a different range. That's okay. But the general idea that all of us agree on is the closer R squared is to 1, the better the fit. So for example, if I go back and do a linear regression, if I decide to run a straight line to try to fit those points, it will give a line to me that is doing its best to fit. So something like 14.39x plus 34.07. But if you look at the graph, you can tell that is not fitting the points very well at all. And if we look back at the equation, right under the equation, it had an r and an r squared. Just so you know, since we're looking at several different models, we are just looking at r squared. Don't worry about r right now, just r squared. So that gives us a 0.58. So is there a little bit of fit? Sure, a little bit, but not very good at all. 0.58 is not very close to 1, so it's definitely not as good a fit as the quadratic. So this is how you need to run these regressions. I'm going to read through it, but if you need more time to copy it, just hit pause. Plug data into Stat, then click on Edit, and do all your data. Plug all the x values in L1, plug all the y values in L2. Then hit second y equals, takes you to the plot data. turn plot 1 on, make sure it's on a scatter plot. Then you will view the points by clicking Zoom 9, which is Zoom Stat. Then you'll go back, then you'll judge the shape of it to decide what kind of regression to do, whether it's linear, quadratic, cubic, or quartic. Then click on Stat, Calc, and then choose whatever regression seems most appropriate. And remember to do the vars, y-vars, function y1. That's the way to automatically get the equation plugged in for you into the graph. Then you'll be able to view the equation that they give and the r squared. Because sometimes you may not know, it may be hard for you to tell. I don't know which one is best. So one thing you can do is do the regression of more than one of them and then compare the r squared. Okay, so here's another set of data. Let's try it here. It says write a polynomial function to model the data. So I've got this data plugged in. We'll go to Stat, Edit. I actually plugged them in L3. I'm just going to shift it over. You don't have to know how to do that. It's just a way I did to help it go a little quicker in the video. But you would plug all the x values in L1, plug all the y values in L2. Okay, so now all my x's are in L1, all my y's are in L2. So my stat plot should still be on. I shouldn't have to turn that back on. Okay, we're good there. I do want to clear out that equation I have from the last one. I don't want it cluttering things. And I need to click Zoom 9 because I've got new data now to fit it. Okay. So hopefully it's pretty clear since we have a change of direction 1, 2 times. It's got this shape right here. 2 changes of shape plus 1 tells me I should use x cubed. So I will do a cubic model. I'll go back to Stat, go over to Calc. You can just type the number 6 if you want for cubic regression. L1 and L2, that's correct. We go to variables or vars, y variables, function y1, and hit calculate, and it gives us the equation. So about 3x cubed, 1x cubed plus 3x squared plus 1x plus a negative 5, or just minus 5. And the r squared is really close to 1. So the r squared tells us we have a very good fit. But we would write this equation as 1x cubed minus 3x squared. So I'm just plugging the a in right here, the b in right here, c in right here. So plus 1x minus 5. So there's my equation. Now the next thing it asks is to use our model to predict the value in x is equal to 7. You can do that one of two ways. You can either just manually plug it in, just plug in 7 cubed minus 3 times 7 squared plus 7 minus 5. That will give you the correct answer. Or, since we've plugged this graph, or plugged this into our graph already, into y equals, if we go to the table, we can just type in 7 and hit enter. So we get 197.95 as the predicted value when x is equal to 7. Just one thing, I'm surprised the r squared was so close to 1 but not 1. I may have done that on purpose, but I can't remember when I got this problem. So if you're getting a slightly different r squared, it could be I typed data in incorrectly, but I think it's all correct. The process is still the same either way, don't worry about that. Then the last part says, use your model to predict when the function will equal 65. So this is different. You got to make sure you're paying attention. Here, they're giving us the x value, so we just plugged 7 in for x and found the y value. Here, they're actually giving us a y value, and we need to plug it into y and then solve for x. So they're saying what's going to happen with f of x, the function, the y, f of x, that's the function, that's our y value. So what's the x value going to be when the y value is 65? So we could take the equation, set it equal to 65, and just hope we can somehow solve for that, but that's going to be fairly difficult. So instead what I'd recommend is go to y equals. We've already got the equation of the polynomial in y1. We'll plug 65 in y2. Because if I look at where those two meet on the graph, that tells me where the two are equal to each other. So if I look at the graph, I suspect I'm not going to see this line because it's the horizontal line y equals 65, because it's way above what we have here. So since we can't see that line, we're going to need to zoom out so we can do that. Or if you'd rather just change your window around to make sure it goes up past 65, you can. I'm just going to zoom out, and that will probably give me enough. If not, I can zoom out one more time. There we see the polynomial again. Ah, good. And there's y equals 65. So where they meet is where that equation is equal to 65. So that will solve this equation for me. So I need to find out where they intersect. So they intersect somewhere up here, and I can find that value with the calculator. So go to Second, Calc. We want to find out where they intersect, number 5. So hit number 5. It's going to say first curve. All they want you to do is try to move the cursor, which is right near the center right now. Move the cursor to where it's really close to where the two of them meet. I know it's kind of hard to see because where that equation is. I went a little too far. We want our cursor to be pretty close to there. So I think I'm closest to that spot. You can see right at the top. Hit enter. Then the second curve, I'm already real close, so I'll just hit enter again. When it says guess, just hit enter. And it tells us they meet at the x value of 5.3. So we can predict that the y value, the function, will equal 65 when x is equal to 5.3. So that answers the question down at the bottom. So we can predict the model will equal 65 when x is equal to 5.3. So last thing I just want to make sure is clear. If you ever look at the data and you can't tell what shape it is, sometimes it won't be as obvious. The best approach is to just give your best guess for two of them and then try both of them. Like on this one, maybe for some reason I thought, well, maybe it should be quadratic. If I go to Stat, Calc, do number 5 for quadratic, I get an r squared of 0.8. So that tells me there is an okay fit there, but it's not as good as the other one. My cubic fit was 0.99. That's clearly closer to 1 than 0.8, so I would want to stick with cubic. The quadratic does some good, but not as much good as the cubic, so we'd want to stick with cubic for that reason. But when you're not sure which model to use, run more than one, look at them in the graph, see how well they fit, and compare their r squareds. Good luck!